Okay, let's get started. Good afternoon, everyone. Welcome to the HEO colloquium. And today we are very glad to have Dr. John Dumbeck from University of Minnesota. So let me give a brief introduction of Dr. Dumbeck. John Dumbeck received his PhD from the University of Minnesota in 2005, and his thesis on orphan waves and acceleration in the aurora zone was a winner of the Fred L. Scott Award in 2006. And he has predominantly been involved in geophysical satellite data analysis research, and more recently, model development. He also has a electrical engineering degree and worked at IBM and Eaton on U.S. Navy ship control systems, and was a CTO for technology company in a previous lifetime during the dot-com era. And he also did flood prediction programming for the National Weather Service in his previous life. So that's a very wonderful life experience. And yeah, welcome again, John. And today he's going to talk about interactions and the characteristics of precipitating auroral electrons in the backscatter and remote sensing atmospheric neutral density. So please take it away.
Hi, everyone. So we're gonna, that's a bit of a mouthful for the title, so we'll just call it Net Auroral Electrons and Friends, and we'll go through a variety of things. There's going to be a story. These are a number of people that have contributed to the talk, to the things in the talk, and we will go from there. So basically, we're going to go through an entire story that's going to end up with the contributions to the net auroral electron flux into the ionosphere by different precipitation mechanisms. But we have to get there, but we're going to take a slight detour along the way to talk about remote sensing the upper atmosphere neutral density by altitude, which comes out of some of the other techniques. And if we have time, we will go through the statistical spectra for electrons from the FAST mission. That's a tool that we're going to be releasing soon. But we'll start with a little bit of background just to get you oriented with the plots. And so first of all, we have a Maxwellian, if you have a Maxwellian distribution, if we're here in velocity space in 1D, it basically looks like that. If we now transition into energy space instead of velocity space, and we have a log scale instead of a linear scale, the Maxwellian now looks like that in number density. And if we now transition from number density to energy density, so even though we have a lot of particles over here, they each don't have a lot of energy. So you end up with a peak in the energy, which is actually related to the temperature. In our case, it's 2 times the temperature is where the peak is. And so that's in 1D. If we're looking in 2D in these plots here, so in these plots, this direction is going to be along the magnetic field line. These two directions are going to be perpendicular. This is going to be anti-magnetic field line. And so if it were isotropic, the color represents the height of the energy distribution. And so you'd end up with something that looks like this. These little things here are wings from the satellite. These are photoelectrons from the satellite that are at nearly 90 degrees. So if an electron gets kicked off the satellite, it'll make one gyro radius and come back into the detector at low energy and at about 90 degrees. And so hopefully that gets you at least oriented. And so a real distribution, if you just have a magnetospheric population coming down, again, this is for its field line is pointing down if we're in the northern hemisphere, then you'll have isotropic all the way around, except for in the upgoing lost cone. So in the downgoing lost cone, these are particles that will be lost to the ionosphere. And then you have particles coming back up from the ionosphere, which are within the lost cones, and these regions are mirroring. And so they're the same going up and down. And how the satellite actually works is you end up with the satellite is spinning, and as it's spinning, basically once every second, but we're using 5-second averages, that as it's spinning, it'll sweep through the energies from high to low, and then it'll start sweeping again as the satellite has rotated. And so you'll get basically 32 angle bins in all different pitch angle directions. And then the contour plots are constructed from those individual data points. And so so in summary, they produce spectra off of these distribution plots. And so the spectra can be either energy spectra. In this case, we have the black energy spectra as basically an average over 30 degrees straight down. And the blue line is a 30-degree average over straight up for whichever bins happen to fall within those. And then you can also do pitch angle distributions going all the way around, which are these. In this case, we have the red ones are in the isotropic side, and then the black ones are the ones on the upgoing side, as this were. And so you can see the upgoing loss cone. And these are on two different energy ranges. One is a low energy range, and one is a high energy range. If you end up with, in this particular case, it's isotropic in the downgoing, and then you have the loss cone in the upgoing. And then on these plots also, you have a this is the ratio of down to up or up to down, where the scale is on this side. So if they were equal, it would be 1. And if it's 10 times as much, it's going to be up to there. And so at high energies, you have more down than up. At low energies, you have more up than down because of backscatter, which is what we will get to next. So when you have electrons coming down, they then cause electrons to go back up. And there's two different types of those. One of those is called primary backscatter. This goes back to Dave Evans and Banks back in '74, where they did a variety of different things. But the idea is that primaries, so this is energy on the here, and this is flux. And so what you end up having is for primaries are the original incident electrons that come in and bounce off of a nuclei and come back up. And those are generally going to have, at least according to their models, are going to have, they can't have energy more than they came down with. And so, and the peak of the energy will likely be about where they came in at, because it's the nuclei is so much heavier. And then you have a decrease likelihood of having less energy coming back for the primary electrons. And secondary electrons, so the primary electrons are dependent upon the incoming energy for this spectra, whereas the secondary electrons, which are electrons that are either knocked off of atoms or ions, or were free electrons that then get knocked into by the incident electrons, and they then knock into other electrons, and you end up having this cascade that some of those end up coming back up. And so the thought at the time was at least that there's a universal background spectra, that it doesn't matter how much, what the energies of the incoming particles are, you just basically take the total amount of incoming flux, and you'll end up causing a cascade that has basically this distribution. And so it's going to be dominated by low energy particles, because that's how the cascade basically works. And so if you put them together, if you had particles that were all coming in at, say, 1500 eV, you'd have the primaries and then the secondaries, and you'd join this universal secondary curve. And so same thing, if you had ones coming in at a 10,000 eV, then you'd have this curve. And so in reality, you have multiple energies coming in. So in some sense, you have to convolve this to figure out what the actual outgoing spectra is. Okay, and so we'll get into that more in a minute. But there's basically 3 different types of ways to precipitate electrons. There's 3 primary ways. There's a few other ways, but one of which is wave scattering. If you didn't have any particles, you'd eventually end up with a double loss cone on closed field lines, because the particles would precipitate on either hemisphere. And so in order to get precipitation, you need to either wave scatter the particles that are mirroring into the loss cone, and then you also need to replenish them. This is also called the diffuse aurora, and it tends to be isotropic, as was shown in the previous slides. You can also get direct precipitation on the open field lines and the cusp and things. Those also are going to be isotropic and mostly Maxwellian. The wave scattered ones are Maxwellian, or actually typically a kappa distribution, but are similar to Maxwellians. And so then the next is a quasi-static potential structure, where you have some sort of structure that is accelerating all of the electrons that are going through it. We'll get into that more in a minute. Those are also called monoenergetic or inverted V. And then the third type is kinetic or inertial Alfvén wave acceleration. And that's another mechanism. We'll describe that again in a moment. But those are the 3 primary ways to do it. Is if you have Alfvén waves in a small enough perpendicular spatial scale, you can get a parallel component electric field, which can end up accelerating the electrons. And so we already talked about the wave scattering one. Effectively, we gave you an example of that. That's just the background population being scattered by waves into the loss cone. But if we go to a quasi-static potential, which we can have a cartoon that looks something like this, where you have a potential in space, the electrons are all going to be accelerated by the potential drop of the quasi-static potential structure. And any electrons that have lower than that potential coming back up in energy are going to get reflected back down, and the ions, of course, are the opposite. So in an upgoing current region anyway. And so in reality, they look more like a U-shaped potential. And so you end up getting most of the acceleration where the electric field is parallel, and you get less of it as you go to either side, which is where the name inverted V came. So this is an example of a spectrogram of a fast pass. And so you get the center of the structure, and then on either side they get accelerated less. And this is also why they're called monoenergetic, because they look very much like they have one energy, because most of the population was low energy and it got accelerated by this potential drop, which is significantly higher than most of the particles had. Okay, and so then the particle, this again causes backscatter, and in the upgoing spectra here, you can see that the backscatter has the exact same exact same spectra going down and up, because the upgoing, everything that came from above gets accelerated above that energy, and everything that is backscattered that has an energy below it is going to get reflected back down. And so if you look at the distribution, you see there's a separatrix basically between where you have the accelerated magnetospheric particles and then nothing in the upgoing loss cone, and then you have exactly the same in the upgoing and downgoing. And so you can end up having the, this is pitch angle, not actually angle as it's drawn here, but you can have the backscatter reflect and cause more backscatter, and reflect and cause more backscatter, and so on and so forth, gradually with lower energy. And so the typical way that people think of these, as we saw in the example, is a very high quasi-static potential, which takes this the background population and accelerates almost all of it. So you end up with this monoenergetic peak. But you can also have low potential structures, which are not higher than the temperature peak. And so you end up with, because again, this is a log scale. So if you had a 200 eV acceleration, that's not going to change the energy of a 8,000 eV particle very much. And so in that case, you'll have a peak due to the quasi-static potential, but you also see the peak from the original kappa distribution. And then in kinetic Alfvén wave acceleration, you basically have the wave is alternating electric fields slightly in a parallel direction, which in itself doesn't accelerate particles. But if the particle was already moving at a velocity relatively close to the velocity of the wave to begin with, it could get a kick from the electric field when it's in one direction and then not be there when the electric field goes the other way, for example. And since the Alfvén velocity, this is altitude, and the Alfvén velocity in day and night is different, but because of density. But you basically have an accelerating Alfvén velocity as you come down in altitude. And so if the electron is in phase, it can basically continually get kicked faster and faster and faster until you get to the peak here. And they're never perfectly in phase, but they can get a different amount of energy depending on how close to being in phase they are, until the Alfvén velocity then drops because density increases dramatically. And so what you then have is that the particles then go faster than the wave and are no longer being accelerated. And so the mirror force then takes over and starts spreading them out in pitch angle again. And so if you look at the distribution, because there's different amount of being in phase, you end up with what's called a broadband distribution in energy. And then you also have kind of like this mushroom shape, because the higher energy ones outrace the wave higher up and had the mirror force acting on them longer than the lower ones. And so you end up with downgoing and upgoing spectra that look more broadband versus the monoenergetic peak that we saw on the other one. However, it should be noted that low potential inverted Vs, or low potential monoenergetic or quasi-static, if you're just looking at the downgoing spectra, which is this black one, it can look very similar to Alfvénic acceleration. So this is an example of Alfvénic acceleration. This is an example of low potential inverted V. The difference you can tell is in the ratio of, at low energy, again, the quasi-static potential is causing it to mirror, and so they're exactly the same, whereas in the Alfvénic case, they're not. And so Patrick Newell had a very well accepted paper in 2009, which looked at what flux was coming from which mechanisms. And he basically was using DMSP, which just had a downgoing spectra. And so he basically had a algorithm that's outlined here, exactly what the algorithm was. But he basically, if it looks for something that was monoenergetic, basically it had to have a differential energy flux or differential flux over a certain threshold. And then if it dropped off quickly, it was called monoenergetic. If it didn't drop off, if there were a number of bins that were above the threshold, it was called broadband. If it didn't meet either of his exact criteria, then it would be called diffuse. Or if it was, quote, non-accelerated, which means that it had a peak energy less than 100 eV or an average energy less than 80 eV, or if it had the flux didn't go over his threshold, which was 1 × 10⁸, then it was also called diffuse. So basically, diffuse was everything that wasn't identified as either monoenergetic or broadband. And one of the things about this, other than the fact that not all monoenergetic look or not all quasi-static look monoenergetic, is that have less than 1 × 10⁸ eV is actually 80% of the data. And so that all gets thrown into diffuse. But his results were basically that 80% of the energy comes from diffuse acceleration, as he found it. And so we basically looked at that using FAST, where we could look at upgoing and downgoing and the pitch angle spectra to determine if it's isotropic or not, to determine which mechanisms were happening in 2018. And we also used his method with the FAST data to compare against. And what we found, first of all, is that getting over 10⁸ is only true in about 13% of the data. 80-some% of the data doesn't meet this threshold at all. And then also what we found is a very small percent. So the top chart here is for day side, the bottom side is for night side, but there's only a very small amount that doesn't have more than one mechanism occurring at the same time. And even if you look at the percentages of mechanisms that were happening, if you take what the Newell mechanism methodology would call diffuse or monoenergetic or broadband, we only found that the mechanism that would associate with those three was only happening somewhere between 35 and 80% of the time. And so there was some mismatch. Now, the issue is that at least with Newell's method, you either had one or the other, and you could mix them together and figure out how much flux total was coming in to the entire hemisphere. Whereas ours, having quasi-static and alphanic, you don't know how much is coming from which. Okay, so we couldn't bin it that way. So that started us on a 6-year quest, basically, to be able to figure out how much flux is actually coming from different things when you have different mechanisms occurring at the same time. Okay, and so this is that quest. And so these are the steps that we need. I'm not going to go through this chart to be able to actually identify all of that. But in short, what you need to do is first determine, or what the method basically does, is you determine the source flux. That is, you determine what the kappa and the temperature and the density of the original magnetospheric spectra was. You then determine if there's a quasi-static potential and what the net flux contribution to that will be. And then you take those two, subtract out so you take the total amount that you see, you subtract out what was quasi-static and what was from the plasma sheet, and you call that the alphanic portion. And so we can do that, although it's a matter of having to identify when the different mechanisms are occurring and being able to identify those different things. Right now, our threshold, so the previous technique, the threshold was 1 × 10⁸. We're now down to 3 × 10⁷. We're working to get it down to 1 × 10⁷, so we can cover maybe 50% or so of the data total and most of the energy. Okay, but we won't go through all this in detail. But okay, so the first step is to take the empirical backscatter, or to figure out the backscatter that's associated with the background population. So once we'd identify the downgoing background population, we need to know, in order to know the net amount of flux into the ionosphere, we need to know how much is going to come back. And we need to be able to know that even when there's other mechanisms going on. And so we need a model to be able to determine that. And so we took all of the times in the FAST data, which is 13 years, and we found all of the ones where there was nothing else going on except for plasma sheet distributions. That is, they fit a kappa extremely well. And so we had like 50,000 events. And we then said, okay, well, this is pretty close to a straight line, and this is pretty close to a straight line. And so we're just going to assume it's a straight line on a log plot, which is a power law. And then we're just going to take all of the data and fit it basically we're going to assume some slope and y-intercept for these two lines, and then take the downgoing spectra, figure out what this result is for each of the contributions from each of these different energies, add them all together, and then compare it to the actual upgoing spectra we see, and then fit these until we get the best results. And so we did that for the 50,000 events or so that we had to come up with the best fit parameter. And so this is the result. And so this is the actual, so this is slope and y-intercept of the line of the primaries and the secondaries. And what we found is that it's not exactly consistent, although there is a fit that if you take the average, the thing is on the primaries, it ends up depending upon the altitude of the satellite. And so what seems to be happening is, for the primaries at least, which seems to make sense, is the primaries, once they bounce off a nuclei and come back up, they also have other smaller interactions which take some of their energy away and also change different things. And so the distribution ends up being different between higher altitude and lower altitude. And so there's a fit that actually works quite well. That is this black line depending on the loss cone angle or the altitude effectively. And so what we find is that the line, this is the, if you take it all the way down to where the interactions are actually happening, and if you go up to the highest altitude that FAST is at, it ends up being actually more even energy because of the mixing. So the secondaries, on the other hand, do not have that effect because they're already mixed, but they do have an effect. So the theory, according to Evans, was that you had a universal background curve that didn't matter about what the energies of the particles coming in were, just the total amount of flux. We find it doesn't have the altitude dependence, but it does have a slight energy dependence. And so if you look at the peak energy of the distribution coming down, it changes the slope and y-intercept slightly, although it has less variation than the primaries do. And so if you take the model that we now have and you take that and compute it and compare the flux level versus what the actual upgoing was, you get basically this percentage error. And so we're within 2%, about 75, we're within about 70%. So I'll take that back. We're within 2% over 70% of the time, and within 3% over 85% of the time. So again, the reason we needed this is so we need to know how much backscatter there would be if we know the background distribution, but there's other mechanisms going on at the same time, because that's going to change the backscatter that we see. But we want to know how much flux is attributable to the original that was there. Okay, so now we're going to go, which is what I just said, basically. So now we're going to go on a little side journey of remote sensing the upper atmosphere, because when we were doing this, we realized that looking at the different altitude, looking at the different scattering, you can tell, and the different pitch angle distributions, you can tell what altitude things were scattered at. And so this is a model. This is not from our data, but this is a model. This is the most state-of-the-art model on the actual density profiles in general of the neutrals in the atmosphere by altitude. So this goes up to about 600 kilometers. And so obviously it varies with a variety of different things, but this is a general approach. And so the orange line here is helium. Basically that dominates above 600 kilometers. And then you have a region in altitude where mono oxygen dominates. And then you have a region here where, of course, diatomic nitrogen and oxygen kind of dominate. And so what we wanted to do is we wanted to take, we're not going to be able to tell all the different constituencies, but the question is, what is the total density based on an inversion of figuring out, if we know the densities of these, how much flux would actually come back at different things. And so we tried that. And we took a model where we basically had these three regions of helium and mono oxygen and diatomic nitrogen and oxygen. And if you put a particle down through it, you'll find that if it's a particularly low energy particle, it will of course collide at higher altitude on average than one that is at 1 keV or at 10 keV. And so what we wanted to do is figure out if we could do that backwards by looking at the particles coming back up. And so again, so if we had this picture of pitch angle spectra, now we're just going to take half of it. We find that if we take the downgoing isotropic spectra and we take the upgoing loss cone and we take a particular pitch angle, we find that, so for example, at the lowest energies, this drop maybe makes up a third of the drop, whereas here it makes up maybe 25%, and here it only makes up 20%. And so if we took a particular, let's say 50%, you would find that the loss cone angle moves depending on the energy of the particle. And we did a couple of examples and found that that's actually true, that the lower energy particles tend to have a higher loss cone, which means that they were higher up for the source. And so we then decided to try to see if we can do this en masse to figure out if we can statistically replicate the data that the models show. And then that would give us an ability to, from orbit, remote sense at least the general characteristics of the neutral density of the atmosphere, which is a very difficult measurement to get because you can't do it with radar or anything like that. You can do it through looking at the limb, by looking through the limb, but that only gives you on the terminator. And you can also get it to some degree or to a large degree by spacecraft drag calculations if you have really good measurements of spacecraft drag, but that only goes down to a certain altitude. So the idea of remote sensing gives us the ability to get to lower altitudes. And so we did that. And so we find that, so this is the total median of all of the data together, just to see that there is actually a slope that goes down as we expected. And our method breaks down at higher energies, and we're still looking into that. But in this region, it seems to work pretty well. And so this is the median, this is the altitude. So this is looking at the loss cone again. So you get a higher loss cone at lower energies. We can then map the magnetic field to determine what altitude those came from. And if we do that, this is the statistics from the database, from all of the different 50,000 events that we use. And basically the different colors are from lowest energy to highest energy, what the altitudes are, and then this is just the statistics. And so if we look at the 25% and the 75% line, we basically get these curves here of where the median, basically the lowest energy collide at about 500 kilometers and go down to maybe 100 kilometers, and at the highest energies of particles. And then we have a spread on that. And so we're somewhat confident that at least this is at least a gross measurement of the neutral density, which is, yes.
Hey, just sorry for interrupting. So could you explain what is RCA here?
What is what?
RCA.
That's the loss cone angle.
Loss cone angle. Okay,
Yeah,
I saw that is, but just to double check.
No problem. I've mentioned it before, but I think I went through it fast.
Yeah,
But yeah, loss cone angle is a proxy for altitude, effectively, sort of. But it actually depends on how much that's what you use to map down to the ionospheric height. So yes, so loss cone angle. Yeah. Okay. And so this is statistics for the entire database. And then these are again statistics, but this is basically the curves we get for the median, and then the top 75% and median 75%. And our data is sparse at high energies again, so that means we don't get down to the lowest altitudes very accurately necessarily at this point. And then this is just a sampling where we took 1 out of every 500 events or something and drew the curves that we had to show what and then these are cross sections of the densities. So you can see, so again, this is nuclei density, just like here, by altitude that we get. And so it's a technique that we don't have a very good measurement of it. Actually, we have very little measurements of them at all. And so having a gross measurement from space is at least a technique that can be used to be able to give this value. And so I threw this in here. We realized they came from this other stuff, but we are now going to get back into the rest of the story, which is the next step, which is if you take the background population, you know how much flux is coming in and out. Now you add a quasi-static potential to it, what happens? And so basically, again, if we have the quasi-static potential, you're going to end up having different amounts of flux depending on how high the potential was. In this case, it's a low potential, about 100 eV. This one's maybe about, whatever, 500 eV and so on. And you can see that we have a problem with the background population when the energy of the quasi-static, or the potential of the quasi-static potential, gets too high. We can no longer determine what the background population was. Whereas here you can determine what the background population kappa and temperature and things were. And here you can actually probably do it as well. But when you're here, you don't know what the population was because almost everything is accelerated. But we'll get into that in a minute. And fortunately, it still all works out. But quasi-static potentials add flux going into the ionosphere by basically 3 different mechanisms. Okay, one mechanism is that it accelerates them, obviously. So as the particle comes down, it gains more energy from the potential drop. It also changes the pitch angle which takes more particles that we're going to mirror and puts them into the loss cone. And then the third thing it does is that it traps the backscatter. So you had a certain amount of energy that was going to leave the ionosphere, but now it gets trapped and put back into the ionosphere. And then the fourth thing it does is that it also, because particles that are coming up and coming down have a variety of velocities, if you have alphane waves, it's much more likely that somewhere in that mirroring process, the electron is going to be in phase with the wave. And so if you have a quasi-static potential, it'll tend to increase the efficiency of the alphanic acceleration process. But in our methodology, that's all considered part of the alphanic acceleration energy, not the quasi-static energy. And so what we can do is we can take our initial kappa distribution, we can drop it through a potential drop and figure out how that affects how much of these three things happen. The only tricky thing is that the separatrix varies by direction. Because if you have particles that are going nearly straight up, right? So if you had particles that are going nearly straight up, then at a particular altitude, this much energy will overcome the potential drop, right? But if you had that much energy and it was at this direction, the parallel energy would only be this much and it would get reflected back down. And so at different altitudes of the quasi-static potential, different angles and different energies will escape. And so that has to be taken into account. And so we do that in our model. This is a graph that shows that basically this is, if the initial pitch angle at the ionosphere was this pitch angle, and the altitude of the quasi-static potential has a loss cone angle of, say, 55 degrees, then obviously if anything that's going straight up, it's only going to need the amount of energy of the quasi-static potential. But if it's at 55 degrees and it initially came out at 60 degrees, if the height of the quasi-static potential has a loss cone of 55 degrees, and the original particle at the ionosphere was 60 degrees, you're going to need roughly 2 times the energy for it to escape. And so you have a variety of energy, you have a certain range of energies where, depending on the angle, some of it escapes and some of it gets reflected. And so within our model, we can do that. And so with our model, you end up taking the original potential, you take a kappa and you drop it through the potential and you end up accelerating the downgoing magnetosphere. So if this was the potential, everything would be accelerated to this spectra. And then that would cause a certain amount of backscatter, and that backscatter has a particular, and a certain amount of it will be reflected. And at certain energies, generally below the energy of the quasi-static potential drop, but somewhat higher depending on its angle. And then you have a certain amount that escapes as well. And so the downgoing spectra will look like a combination of this green line and the red line. And the upgoing spectra will look like a combination of the blue and the red line. And so obviously this causes a discontinuity at the quasi-static potential, which nature doesn't like. And so if we draw in basically a just linear diffusion, then it would look more like this, which is basically this is obviously at a different energy, but that's roughly what you get when the shape that you get when you have a quasi-static potential. And so with our model, we can do all of this. We can figure out how much net flux is added by having a quasi-static potential at a certain energy relative to the temperature of the background population. And so if we do that, this is the quasi-static potential drop over the temperature, basically. And then this, we'll start with this graph. This is the percentage of energy that relative to the NIA stands for negligibly accelerated isotropic distribution. That is the background distribution. And so obviously when you'd have almost no potential drop, you have no energy from the quasi-static. And 100% here is where the quasi-static potential adds as much energy as the original population had. And that tends to happen somewhere around 0.1 or 0.2, where the potential structure is 0.1 or 0.2 of the temperature. And these different lines here represent the altitude of the quasi-static potential structure. And so 85 would be a very, very low potential structure, almost on the ionosphere. And 5 would be generally something like 6,000 kilometers or something like that. And so fast is generally about where it's like 30 kilometers or something. But you get different, it depends upon how much gets to escape, because the higher it is, the chances are more are going to escape because more of the energy is parallel. And so this is the same graph, except on a log scale instead of a linear scale. And you can see that by the time you get to where the potential structure is the same as the temperature, where the potential drop is the same as the temperature, you have about something like 10 times or something about as much energy coming from the quasi-static potential than the background population. And so if you do that for different kappa values that all have peaks at the same temperature, you end up finding that generally you have about you have about 5 to 10 times as much energy coming from the quasi-static potential structure than you do from the background population once you get above about 0.5 or 0.7 times the actual peak of the temperature. And so what that allows us to do is, therefore, if the potential causes us not to be able to see the background population, we know that virtually all of the energy that we see is coming from the quasi-static potential and not from the background population anyway. So in our case, we just call it all quasi-static potential. Our current estimate is that probably due to this effect, about 5% of the quasi-static flux should probably be contributed to the background flux instead. But when it's a lower potential, we can obviously separate them. But when it's not, we can't. But we're calling that all quasi-static potential, and that's mostly true. It's within 10% or something like that. Okay, so finally we can put this all together, and we can figure out how much comes from the different mechanisms. But in order to do that, first we have to be able to identify what the background population is and what the quasi-static potential is, and we came up with a technique to do that. And so the background population you can usually tell pretty well by looking at the perpendicular direction, although not always, but most of the time. And that's why there's the giant flow chart that we showed at the beginning of all the different ways to do it. But in a simpler case such as this one, for illustrative purposes, this is the spectra of all three the distribution of all three mechanisms occurring at the same time, where you have an intense background population, you have a quasi-static potential, and you have alphanic acceleration going on. And you can see from the spectra, it'd be difficult to tell exactly what's going on from the spectra or even from the distribution. But what we can do is we can take a differential distribution where we take down minus up, and we end up with this distribution. So if there was more on the upward side, it gets plotted over here. If there was more on the downward side, it gets plotted over here. If there's more on the upward side, it gets plotted over here. And we won't go through all the details of all the different structures in here at this point. But what's important is this blatant difference where you have more upward here and more downward here and here. And what that is caused by is the quasi-static potential, because what happens is that even at perpendicular distances, there's a very small amount of alphanic acceleration happening between when it crosses the satellite and it returns to the satellite. And so for mirroring particles, the electron first is going downward, and then it mirrors and comes back upward and passes the satellite again. And in so doing, it in that time period, it got accelerated a little bit. And so you end up with more upgoing than downgoing, because the particles that were downgoing got accelerated slightly in the round trip. But in the backscatter particles, you end up, they're coming upward, passing the satellite, mirroring off the quasi-static potential, and then coming down. So you end up with more downward energy than upward energy. And so basically this separatrix allows us to be able to determine exactly what the quasi-static potential is when we have multi-mechanisms going on. And so this, I won't go through this next page, but this is the technique in more detail. And so you find basically this distribution. If we plot this plot instead of in a polar plot, we plot it linear, we plot it as a flat plot. this line becomes a straight line here, where there's a differential between upward and downward. But we identified the different regions, and we're therefore able to determine what the quasi-static potential is. And we also can identify the background population. And so with those two things, we then can use our models to calculate how much net flux came from the background population, how much net flux is added by the quasi-static potential, and then the differential we call the Alfvénic contribution. And so putting that all together, these are the results that we have. And so basically, this is the total amount of flux in hemispheric power. And again, this is sunward direction. This is midnight. This is dawn. This is dusk. There's a total of, this is just the total amount of ergs per square centimeter per second, basically on average over the entire mission. And so what you end up with is a total power of about 32 gigawatts over the hemisphere. So all the other scales are the same. The total one is about 3 times the amount of the other ones, just so that the color scales are similar, but the other ones then all add up to this. And so what we have is we have quasi-static. This is where the energy from the, so this, even when multiple mechanisms are occurring, how much energy is coming from quasi-static, how much is coming from wave scattering, or again on the open field lines from direct precipitation, and then how much is coming from Alfvénic. And then for things less than 3 times 10 to the 7th, those are what we call weak events, and this is how much flux is coming from there. And then there's certain ones that don't, our criteria it doesn't fit. We can't identify what's going on, but that ends up being a very small percentage of the data. And so what we find in general is that of what we can detect, which is the higher flux events, which is about 30% of the data at this point, we end up with actually most of the data, most of the power comes from quasi-static, followed by Alfvénic, and then finally by diffuse or wave scattering. Although the weak events also have a significant amount of flux, and it's likely that a lot of this comes from diffuse effects, although we don't know how much until we actually lower, because as you lower the thresholds, if we just look at the data, some of them still have quasi-static and Alfvénic acceleration going on, and you can kind of tell by the locations. And so I'll summarize this in a second slide, but before we do that, I'm going to show this data, which is the percentage of where we see the different types of flux. And so this is, again, the total flux. So this is where the total amount of flux actually occurs. This is assuming everything adding up to 100% in each bin. What is the total energy flux percentage by mechanism by location? So for example, if you add up all 4 of these, you get to 100% in each bin. So most of the flux from here is coming from quasi-static. Most of it here is coming from Alfvénic. There just isn't very much, and so on and so forth. Whereas this is then the occurrence frequency of where we can identify wave scattering, significant wave scattering, or quasi-static, or where more than 10% of the flux that we see is Alfvénic. Because again, because we're taking the total minus these 2, there's always going to be some difference. And so it might be, 1% or something. So we're not calling that Alfvénic, but where more than 10% of the flux coming down is greater than is Alfvénic, we say that we have Alfvénic occurring. And then this is the weak percentage. And so in summary, first of all, being able to determine the amount of flux attributable to different events, the different precipitation mechanisms, is basically feasible if you use the full distributions, although we're still vetting minor parts of the algorithm to make sure everything's working exactly right, but we're still working on that. And different mechanisms obviously dominate in different locations. From our initial results, wave scattering or diffuse precipitation does not appear to dramatically dominate the total flux. Okay, and actually quasi-static and Alfvénic seem to contribute the most, with diffuse being less prominent. Although again, the weak events, which we currently aren't able to analyze, are substantial. And so if we assume, so this is an assumption, but if we just take a general assumption and we say half of the weak power is wave scattering, a third of it is Alfvénic, and a sixth of it is quasi-static, then we end up with 11 gigawatts for quasi-static, 11.2 for Alfvénic, and 10.3 for wave scattering. which makes them all roughly comparable contributions. But again, in order to do that, we have to lower the differential flux limit so that we can address that. So this ends our main story. We can either take questions on that now and then go to the spectra stuff, which is just like 5 minutes, or we can do the spectra stuff first, which we prefer to do.
Well, yeah, maybe you can just continue, and then we can come back to all the questions.
Okay, that sounds good. Okay, so so the last thing we're going to get to is, in a physical sense, it's important. In some sense, this was a quest to determine what the different contributions of the different mechanisms were or are for the energy input into the ionosphere, which is useful from a physical point of view and very interesting. But what modelers actually want is that's helpful for modelers, but and for physical understanding. But a lot of times what modelers want is they want to know what the actual energy spectra is that they need for their model. And so what we did is we developed a tool where you can take whatever criteria you want. We'll go through what the different criteria are, and it will go through the entire FAST mission and figure out when those conditions were true, and then it'll statistically figure out what the average spectra would be, both the downgoing spectra, the upgoing spectra, and the mirroring spectra. And so in general, what it does is it's going to give you either the downgoing, well, either or, and the downgoing, upgoing, or mirroring spectra by condition and location. And it uses 1 degree spline distributions from the FAST mission to be able to determine this. And so it's as accurate as we can get. And the statistical spectral database, so basically it can provide the mean plus or minus 1 sigma, the median, and the 25 and 75% values is what it can do. It gives you the downgoing, upward, and mirroring. And it can also normalize by taking all the spectra and just averaging them, or taking the median of them. Or you can normalize them by the energy flux of the spectra, or you can normalize it by the number flux of the spectra, depending on what you're trying to accomplish. And so different, so raw distribution is not, because if you take the raw ones, then the more energetic events are obviously going to be counted higher, but it might not be a typical spectra necessarily. And then you can sort the database by location, MLT, ILAT altitude, by the ionosphere conditions, the solar zenith angle, F10.7, season, that sort of thing, and also by the magnetospheric conditions, KP, AE, DST, storm magnitude and phase, solar wind magnetic field magnitude and direction, solar wind velocity, temperature, density, and various combinations of them. At least that's where we're going toward. You can, in our version, the version that we're producing for people to use, we're putting some of those in at this point. And then MI coupling conditions, that is, which precipitation mechanisms are identified, what the characteristic energy is, what the field aligned direction and magnitudes are. And so we have that on our servers at the moment. And the idea is to make a virtual machine that everybody from the community could be able to log into and use. We worked with the university administration here about hosting that, and that became a whole administrative nightmare of they want to be in this thing, but then we were the first people that wanted to be able to do this, evidently, in the entire university. And so they needed to figure out a system of how to be able to do that, which took them 3 months to figure out. And they decided that the IT people don't want us to host a machine that has a website, and they don't want to be responsible as the university for funding a virtual machine on their servers ad infinitum. And so what we ended up with is a distributed method using a thing, I forget what it's called. What's it? Docker, yes. So it's called Docker. And so Docker is a virtual machine that runs on your local machine. So you download this package and then you run it, and it runs a virtual machine on your own machine that's self-contained. And so then you log into a website that's hosted on a special port on your own machine, and then it accesses it that way. So it's like doing it remotely, but not. And so we've had to rewrite everything in order to work with this, and it now exists. And I'll show you some of the things. And so if you're interested in it, let me know. We're still putting some of the finishing touches on it, but at least exists. It does take about 4 hours to set up on your computer. Not that you have to sit there for 4 hours, but because of how it's packaged, it has the data comes as a package, and then when you first start it, it has to load all that data into the database initially. And so the whole process takes about 4 hours or something like that. But once you have it, then you can just run it. And it does take up about 120 gigabytes of space. But and so this is from our in-house versions, but these are examples of the statistical spectra. And so this is just an example of looking at a particular location where you look at only alphanic and only dark foot points. And in this case, we're plotting I guess it's not labeled here, but we're plotting the mean and the median, and then the 25% and 75% lines and the 1 sigma line for the spectra for all of the events that happened with these criteria. And then this is plotting the upgoing and downgoing and mirroring for a different set of criteria. And then this is plotting the quasi-static and alphanic and wave scattering ones, where it's just plotting now the median and the 25 and 75%, whereas this is just plotting the median, for example. Or you could break it down by different ILATs in the same local time region, for example. And so these are just examples of the type of plots you could get. Or you could get really refined if you just have a model where you just have, a particular event that you're trying to characterize. You can find all the fast events that met that, and then you'd go through just, if you just do statistically look at, the few events that meet those criteria. And we're going to have, it's not implemented in the virtual machine version, but it will be eventually, where if there's less than, say, 30 events, we'll have the option of where it'll just output the 30 events for you, so you can look at those 30 events and see what they are, in addition to doing the statistics. So, and so then this is just another example. For example, now we're looking at different local time regions where noon would be here, and we're looking at different spectra. These are all the downgoing spectra, raw, so it's not normalized by anything, for different mechanisms, for example. And these are sunlit foot points. These are dark foot points because you're on the night side. And you can do the same thing going around an MLT for only the quasi-static, only the alphanic, only the weak, or only the isotropic or wave scattering. And now we're looking at different latitudes for the different mechanisms for the. And so those are just examples of the types of data you can get out of this tool. And then this is actual examples of the tool that you'd get on your website. And so basically you'd click on which particular conditions you'd like to do. It then will bring up where you can say you want it to, MLT, for example, be between or above or below certain ranges, solar zenith angle, what your mechanisms are. And so depending upon what you click here, you're going to have different things to be able to set here. And then once you do that, it will then give you the amount that fit that criteria in the early mission and late mission. And that's about halfway through the mission. The issue is that in between the early mission and late mission, they use different energies for the 47 energy bins. And so you can't directly bin the different energy fluxes from the early mission and late mission. And so it gives you the amount of events that you see in the early mission and late mission. And so then you say which statistics you want to see, if you want upward, downward, or mirroring, how you want to normalize it. And then if you want early, late mission, or late mission, or both. If you have very few statistics, you can put both together, but it's not scientifically meaningful necessarily because the energy bins don't exactly line up, but it's capable to be done. And then this is an example of the plots that come out. So again, you have the mean is the red line here. The median is the blue line. This is the 25% and 75% lines. This is +1 sigma. This is -1 sigma. Sigma is bigger than the median or the mean. So, and then we're taking care of this. This has to do with the sweep frequency of the data. And so the top energy bin a lot of time actually contains data while the plates on the instrument were sweeping. So it got some of this lower energy flux was counted as higher energy. So we're taking care of that, and that'll be done when released. But that's basically that. And so that's the end. Thank you.
Thank you, John. That's really, I can't tell how valuable this product will be. But let's just go over the room and the people online. Any questions for John?
I'll go back to the summary of the main part here. Okay.
Sure.
There we go. Okay.
Yeah, I know we are over 1 hour, but since we got the technical issue. Okay, Bill, please. Yeah, let's stay for a few more minutes.
John, one of the main takeaways I get from your work is that the simple model that Newell developed, the criteria for classifying precipitation based on sort of different mechanisms, while simple and useful as a starting point, may actually be misleading if you don't look more carefully at what's going on. And I think you showed that pretty clearly here. One of the questions I have, you didn't say anything about this, and maybe it's not important for your categorizations, but does the parallel distribution, in altitude along the field line of the quasi-static potential drop influence your results? Did you have to assume anything about that distribution?
No, we don't actually, because it's really where the quasi-static potential starts, what altitude it starts at, because because that threshold is where the mirror force takes over, right? And so it's where you're being accelerated or you're not being accelerated is what matters in the altitude as to if it's going to escape or not. So that's basically, at least most, I guess, now that I think about it, that's probably not true. Although what the data has shown is basically the, half of the potential drop is within, 100 kilometers or something like that at the bottom. And then the other half is distributed over several of an RE or something like that is generally. And so that's kind of what we have in the model. We could test to see how sensitive it is to that. I don't think it's overly sensitive, though. It's not in the model as far as differences, though, at this point. So we'd have to test that.
Okay.
As far as the Newell thing, I think Newell's method was simple, and obviously it's 15 years before now, right? And so we've had 15 years to be able to use it. And I look at it as, like I'm looking at the pure states of the acceleration, and he's looking at mixed states. And so what he identifies as this or that, a broadband or monoenergetic, maybe it's not all, maybe the broadband isn't all alphanic, but it's all consistent, and it's the amount of energy in it is a mixed state of different ones, and that energy all adds up, which is what like Ovation Prime people are interested in, is the total amount of energy and the characteristic energies and things like that. And so I think it's accurate. It's just that it's using mixed states instead of the pure states of the actual mechanisms.
Yeah, I agree. Thanks.
Mhm.
Yeah, I have a quick question. So it looks like in the statistical maps you showed, it only goes down to 60 degrees. So do you have any coverage below that?
Fast generally turned on at 60 degrees. We do have some data that goes down to 45 degrees, but it's only for part of the mission, and so it doesn't have as good of statistics for everything else. So we didn't include it in the plots, but we could do that.
I see. Yeah, I'm just curious because this latitude range also implies like the level of the auroral activity or storm levels that you will be looking at.
Right. And so the plots that I showed are for the entire mission, right? And so we can subdivide it by, storm phase and things, and storm intensity and things like that as well. But this was just the general overall statistics. But you're correct. We should I have to think about the, non-evenness of coverage of the lower latitude stuff to include it. But particularly for diffuse, there might be some that goes down below 60.
I see. One last question. So in that statistical spectrum, which we certainly need to talk more afterwards, do you make any assumptions about the function form?
No, it's literally just taking all of the, whatever flux there was at each energy bin and averaging that energy bin for all of the different, it finds all of the different events, and then it just either averages or takes the median of each individual energy bin and gives you the spectra. Oh, and we are adding, it's going to give you the total amount of flux for the spectra.
I see.
Or the median and the mean and all that sort of stuff too. So we're adding that, but and so that's what the normalization then. So the normalization determines how to weight the different points before we take the median or the average or whatever.
Gotcha. Yeah. Like I said, I still need more time to talk with you and learn
Right.
about this product. as we discussed earlier in email, yeah, on our side, I have been trying to get a spectrum from the models, and I hope to compare with this data product from your side. So yeah, let's just talk more afterwards.
Right. You can do that, certainly.
Okay. So do people have more questions for John? People online? If not, let's thank speaker again.
Thank you.
Is that the raise hand or you're trying to applaud?
Trying to applaud. Thanks a lot, John. Really nice.
Okay.
Okay, great. Thanks, everybody.